Okay. Thank you. Thank you for to be here. And let me start. Let me start with the lecture. Okay. Um, Let me reconsider again the last lecture of the last slides of last lecture of last time, and let me let me look here what happens now with the theorem and with the MATLAB. Yeah, as I told you last time, we concluded more or less here, which we can see here exactly that we have the pair AC. This means the system, but in the context of the observability, characterized by matrix A and matrix C. Do you remember the test, no? Which was I included here, exactly here. Now, for linear, time invariant, and then for linear time variant. We can see in both, linear. The keyword is linear. We have basically to do, let me say so, with two matrices, with two structure, A and C. Here, not depending on T, and here depending on T. And we concluded last time saying that, of course, we have the dynamics of the error of estimation, which depends again of L and C, but in the structure of the observer, everything can be managed. Let me say managed using a matrix L, which basically allows to place the eigenvalues where we want, where we want. In fact, this theorem says that if the system, which is characterized in terms of observability by the matrix A and C, is observable, then the eigenvalues of A minus LC, exactly the eigenvalues which characterizes the dynamics. Do you remember in math 1, the solution of the differential equations is characterized in its dynamics by the eigenvalues of the matrix, or let me say more easily, the exponent of the exponential functions. But if you remember a bit in math, if you don't remember, it does not matter. Now we will see with MATLAB for the students who is not habited with this language, students who belong to different courses. We can see that MATLAB can calculate exactly these parameters, as I told you, which are the eigenvalue of the matrix, which matrix A minus LC. Exactly this. For the engineers, it's almost clear. For the rest, probably totally unclear, but it's not relevant for the goal of this course, because we will see that we try to implement MATLAB can help us. Then the eigenvalue of A minus LC can be placed arbitrarily. Of course, the theorem works basically also in the other direction. Here is formulated in one direction because it's what we need. I mean, you remember, we tested the observability, and then the idea is to clarify today how I can calculate the matrix L and how I can build the observer. And then we will go ahead the next week in particular, but also today, I hope to introduce a little bit the limit of this observer in order to introduce the advantage of a Kalman filter. Of course, I have to tell you about the discrete structure, because Kalman filter, at least our Kalman filter, is discrete. Of course, again, if I can place arbitrarily the eigenvalue of A minus LC, we say that the system is observable. It works also in the other direction. Now the proof, as I told you last time, is a little bit complicated in bachelor because we it's more complicated also for students from different background. Therefore, I will tell you about the proof with MATLAB. With MATLAB, this means let me open MATLAB now. And then I try to clarify also this slide here, which last time I skipped. You remember this thing. I open the file, I will upload the file for you, and then uh, we will see it together. Look here, in this second formulation, we have an if and only if. We can see here this theorem, let me say, consider also the results in the other direction, as I told you here. No? But everything is correct. Here is formulated, uh, let me say, in the sense that if we have a system observable, then I can place. Because it's, let me say, this formulation follows directly from our lecture, but also, as I told you before, opening this slide here, it's going also in the other direction. Therefore, if and only if. If and only if means if I can place the eigenvalues of the matrix A minus LC using L design matrix, the system is observed. It seems to be complicated, but with the help of MATLAB, I try without this formal aspect of the proof to explain a little bit the proof. It's not necessary for the project, for the rest of the course, but could be nice to look together at this implementation. Let me look at MATLAB and let me try to open one file which I will upload. Okay, about MATLAB last time, I tried to tell you something. A few words because not all students know MATLAB. Again, if you click twice on the icon, again, if you want to work with MATLAB, send me an email and then I will forward to our technician for let me say, for the password to access for the formal aspect in order that you will be able to be able, let me say so, to be able to use this software or that this resource in the remote from home. We have licenses, the license for all toolboxes in MATLAB. Please use it. We spend each year 30,000 euros, no, for all licenses. It's a very, very strong tool. And yeah, it's in the field of research, but also in the field of um, also let me say, implementation is extremely useful. We obtain interesting results in using Kalman filter, but using also different tools which came from my course. It's also in field like psychology, economics. When I come back to Lunenburg next week, slowly I will try to organize seminars. I will invite you, some student from psychology, economics. I hope that they will be able to able, of course, to tell you something about the possibility which can offer, I would like to say, our knowledge of system theory. Okay, again, this central part is the command window, the trivial thing which I told you last time, 1 plus 1 equal to A and S means answer, isn't a variable, or, well, why not? Because if I write 1 plus 3 equal 4, we can see that A and S change. We can see, yeah, sometimes we say variable, name of the variable, or parameters. We can see on the right part, in the workspace, we have the parameter a and s is active with the value 4. I can define another variable, for instance, q equal 3 plus 4, just to understand. And then we have a q, a new variable, another variable with the value equals 7. This command window in the command window, we can call software, we can call programs. We will see during the semester. We can see here the software which we have here. For instance, I don't know if I don't have time in this course to tell you about PSO, even though this PSO particle swarm algorithms is useful also for Kalman filter, but in bachelor is a little bit difficult to tell you about that. But in the project, we can try to apply or to integrate different algorithms. Also, PSO is one of the algorithms which can help Kalman filter, because Kalman filter needs to be tuned. But let me go ahead with the lecture of today. Yeah, this means you can see here a very complicated, not so complicated, but complicated software with the structure of the software, which we can see for loop. We can see here, let me see, while loop. At this moment for you is difficult to follow me, the engineers probably, yes. But just to show you that MATLAB offers a lot of possibility. In particular, when I will introduce Simulink, we will see that we can describe, we can simulate also very complex dynamical systems. Okay, we can see here the path. Last time I told you, at this moment we are in this path. There's the window structure of MATLAB. But here we have the current folder. In the current, excuse me, we have the current folder, which is basically identified. Let me say so. Here we have in the support F. Let me say. And then we have the path. That's a window. Probably this, I don't need to spend more words. And here we have the files which are present in the current folder. The current folder is variant PSO first example. Okay, now I have to move in our of course, in the folder which I have the material of today. Let me see. I have so many material here. Okay. Let me see. This is the Windows system. This means no problem for you. I don't have to clarify what I am doing. I am moving through the folders in order to find the material. Part of the material I already uploaded in my study. Now I would like to upload something more. Yeah, MATLAB course. Okay, now we can see that I changed the path. You can see here now Windows, because I am looking for the material of today, but I don't find it. Let me see here. Yeah, it's here. Let me open, for instance, this here. If this is our system, our software, let me click twice. We can see here, no? Yeah, it's one of our software, no? Exercise 01 m.m. Dot m means MATLAB. No? I don't know why it's 01m, but dot after dot say this nomenclature says to us that in MATLAB file. Okay, let me upload in MATLAB in my study this, because it's exactly what I told you now. So you have also this one. I don't need to share, but we will find in my study also this. No? Okay. Is in my study. Okay, let me clarify a little bit this software. because is connected with the observability and is connected with what I told you until now, also in particular last time. Do you remember this? The system here is exactly the system. The first example it's not the first example. The first example was the DC drive. I think somehow I have also here the DC drive. I don't remember. Uh, yeah, it seems to be DC motor data I see in the list of the files under current folder. But if you remember this, is exactly the example in which I try to introduce the concept of fully observable, uh, in general, the observability um, concept. About the fully observable, we have a different possible definition, but now we can clarify practically what I told you also last time. Look, um, what I am doing now, I am considering again this example here in which I am measuring x1. It's exactly what I told you many times last time and before last time. Here we have the matrix A and B of the system. Again, the matrix B is not relevant for the observability, but we will see that I will use because I don't remember probably I used this example also to build an observer. I don't remember. Let me go ahead together. Very important that at this moment you have the matrix A, but we can see here the matrix C. It seems to be that here I am measuring the variable x2 because probably at the end of the lecture last semester, some students, I considered after measuring x1, the measure x2. This means let me change for you in 1, 0. You remember, C is the map of the sensor. This means C characterizes what I am measuring. If I write 1, 0, this means that I will take x1. Do you remember the lecture of last time? At this moment, forget these three information. We will reconsider in 10 minutes when I will try to design the observer. Matrix A and matrix C of the system, in particular C 1, 0 means y equal x1. Let me write here as a possible comment. No? After this symbol here, percentage, everything is in a comment. This means no meaning for MATLAB, a meaning for us, but not for MATLAB. Then I would like to say, if I consider C equals, so we clarify again what I told you also last time and before last time. Then let me write quickly. So I am measuring x2. So it's clear when I change later. Look, in MATLAB, we can use, given the matrix A and C, I gave the command OBSV in order to calculate the matrix of the observability matrix, which do you remember? In this case, we have just two states. It's C, semicolon, C multiply A. I will show you the structure of this. And directly, I can calculate the rank. Now, let me skip this comment here. I don't comment at this moment now. Let me start to show you what happens until here. So we will repeat a little bit practically what I am doing and connect it with observability. I don't know if we will have some errors because I changed something, but at this moment it's important just until here. Therefore, I didn't put here any semicolon. No? If I put semicolon, I don't see the result in the command window. We will see directly this result here. Let me show you. Mm. We have many things that at this moment no particular meaning for us. But look here. You can see OB, where is OB, rank of this matrix equal to, this means full rank. I come back to the lecture in order to show you what I intend with this. And in the same way, if I build manually the observability matrix in accordance to this test, which is a theorem, C semicolon, C multiply A, I have the same result. Let me go a little bit more in depth on this, opening again the lecture. Yeah, you remember this test. This is the observability matrix. Isn't a theorem. I didn't demonstrate that theorem, but I present it as a theorem because if I say the condition is necessary sufficient, of course, this is the language of a proposition, language of a theorem. Full rank means that we have that no rows, or better to say, the rows of the matrix are independent. For not engineers, a little bit difficult to understand this concept here. But basically means, let me come back in MATLAB, in order to clarify also for not engineer, what is the meaning of this. Look at the matrix. The matrix is C, semicolon means we will start with the second row, C multiply A. You remember last time I told you that we will stop up when A is multiplied n minus 1, is up to n minus 1. N is 2 because n is the number of the state. And this means the matrix, the observability matrix, consists of just two rows. This means consists of just two columns, we will see now. And this C, first row, let me say, and the second row is C minus multiply A. The meaning is of this matrix is to check about the possible connections between, let me say, the dynamics, the equations, roughly speaking, of the system. Do you remember? That's I clarified last time. I tried to. Look, this is the observability matrix. If you remember in math, we have two rows and two columns which are independent. Now, for the non-engineer, it's difficult to understand or to follow me what is independent. But in any case, we have the connections. For students in psychology, is clear. It's difficult to remember or to have in mind this concept here from high school, assuming that in high school was done. But it does not matter. We have connections everywhere. We have a connection everywhere. And what is the meaning everywhere? For all possible states. In fact, look what is the difference if I write here instead of 1001. Do you remember we discussed a lot last time? If I measure x2, I cannot have information about x1. This means the system is not fully observable because I can have information about x2 because I'm measuring. Trivial. If I measure, I have information. But about x1, I don't have it. Do you remember? We don't have connection between the dynamics 1, let me say, related to x1 to the x2. I mean, if I measure x2, I cannot have information about x1. Do you remember? Let me share you the slide again. For the engineer, a little bit boring, but I received a couple emails to proceed slowly or to repeat again the concept. Look at this. No? Here is observable because if I measure x1, it was the example as before. I have information about x2 before, because of this connection here. In this case, excuse me, in this case here, in which I measure x2, we can see here 0, 1. In this case, it was 1, 0. Yeah, the instrument is here in x1. I have information about x2. Exactly what I show you mathematics in the sense using math. Here, if I measure X2, the matrix C, which maps the sensor structure, is 0, 1, this means this instrument is here. Of course, I have information about X2 because I'm measuring, but no possibility to get information about X1 because X1 in the structure of the description of the system, no connection with X2. I mean, X2 is not present in the second equation. We can see here. Okay, let me show you this in MATLAB. It could be that I will have some error, I don't know, but let me check until here, as before. Let me see what I have. Yeah, no problem here because of course I changed something. But look, now we can see that the rank is 1. And we can see that it's not as before that the rank, we have two different way to calculate the rank. Here directly with MATLAB, here using the manually the definition. I mean, this OBSV, the argument are two argument A and C. If you look help OBSV, we can clarify what this command meant. OBSV, né? Yeah. Compute the observable matrix. We can see this is in a function with two arguments, A and C. Né? But of course, you can build also manually. We can see here exactly what I put in evidence now. The rank is 1. Let me look at the matrix. It's interesting. Before, we don't have this 0, 0. You remember I told you at the beginning, I told you at the beginning that observability already 2 weeks ago means connections. And this is related to the full rank of this matrix here. The full rank of this matrix. Basically here, we have just one relevant column, just one relevant row. Because 0, 0 something it seems to be collapsed in the column. Relevant is 1 minus 1. Just try to clarify a little bit, very roughly, the concept of the observability. We don't have connections between the two dynamics. Dynamics is 1 and dynamics 2. I try to clarify graphically last time here a little bit how looks like the observable matrix. Okay, let me go ahead with the easy example at the moment. At this moment, let me go here. Reconsider this. The case in which I have the observability. At this moment, forget this. We will see later. Look at this. The function plays, try directly to solve, to remember last time very quickly, I showed you the idea to calculate L. I will come back again on the lecture last time. Of course, in the project, you don't need to do manually. Plays, solves, I show you what. Let me come back. Sarah, you have a question, excuse me. You can also interrupt me because sometimes I'm concentrating on the material. I don't see the hands. In this case, your hand.
Yeah, sorry,
Yes.
I just have a question with the writing in the line where you say observe or define the observability. And so just what you had it marked just a second ago. Why do you put C multiplied by A in the next column? Does it have a meaning, or is it just so why is it in the next column? Couldn't it be after C?
Yeah, I tried to explain. Thank you, Sarah, for
Oh,
this
sorry.
question. No, I tried to
Maybe I
explain.
haven't quite understood
Very,
it.
very nice because for students who does not belong to engineering category, it's very
Okay.
important to clarify everything. Please pay attention.
Yeah.
I'm here for everybody. This means it could be for the engineer It's something new, but we are here for everybody. This is the meaning of complementary. Then I will do different task to engineer in the examination. Is allowed, and because otherwise it's not fair. No? It seems unfair, but it's fair because the background makes sense if I have in a course in which everybody could could participate. Okay, thank you, Sarah, for this question. What I wrote here is just what I try to explain. Let me show you again. Before last time, very quickly, when I introduced this slide here with the test. Now, I wrote test and I didn't present this result because in the result. Why the result? Because I used to judge if a system is observable or not. Is the system is observable or not? Is stated in case the system is linear and time invariant. It's written in red using this test here. Now, really, the test came from a theorem. I don't remember, in some literature, a theorem, in some literature, is a proposition, lemma, it doesn't matter. But in all these cases, we need a demonstration. Because otherwise, you can say to me, why this is my test? Why I have to trust the test? I don't have in this course, in particular in this course, time to show you the demonstration of this theorem. In fact, I didn't present as a theorem, just a test. But I try to explain. Let me re-explain again, and let me come back to your question. Before explaining a little bit, before explaining, probably it's better to come back to your question. Look at this. The first two row, you use exactly the row, are characterized by C, first row, and by C multiply A, the second row. Why, basically, your question is why once I clarified, I used this test. Why I stopped just considering two rows, C and C multiply A. C as the first row, and C multiply A as the second row. First of all, in MATLAB, the rows, let me say, I identify the rows using a semicolon. Let me come back to MATLAB. C semicolon says that the row, let me say, is ready. I mean, after the semicolon, MATLAB understands, let me say, understands that they have to start with the second row. Question, why I'm considering just two rows? And then I try to explain again the sense of this observability matrix without a strict demonstration or the rigorous demonstration sufficient, necessary, forget this, but it is, I mean, in literature, you can find a real demonstration, mathematical demonstration. Why that? If you look at the structure here, assuming that we understand and we agree that this is an observability matrix, in order to agree, we have to look at the theorem. I don't have time. But believe me, believe me, why I'm stopped using just two rows, C and C multiply A? Because if you look at the last, very important now to clarify the last. The last is C, which multiply n minus 1, in which n, it's a shame it was not precise, at least probably before, I don't remember if in any case, I told you about n. Should be necessary probably to recall here what n is. N is the number of states. Remember the concept of states. The concept of state is related to, or the reflect the number of independent energies. Independent is a little bit difficult, but you can find the literature also why independent. But let me say energy, a little bit more easy. This means we have in this system two kinds of energies. Do you remember in the DC drive, the model for engineer is easy, but also for the other students, I tried to clarify that we had two kinds, or three eventually, But let me consider the reduced system. We have two kinds of energies. Electromagnetic energy because of the coils, and the kinetic energy because the motor runs. In this case here is more abstract, could be everything, economics, psychological. I will invite you in a seminar in which we modeled and used Kalman filter in the description of feeling in a chaotic system, which is bipolar diseases, but I will invite you. I have two states, but if the last line, or the row, you can call as you want, is characterized by A up to n minus 1. If n is 2, we have two states, two energies. Of course, n equal to minus 1 means in this structure A up to 1. Therefore, I have to consider just C is the first one always, and C multiply A as the second line. Because the length, let me say, of the number, better to say, of the row is characterized by n minus 1, which is the exponent of A. The meaning of this observable matrix is to build the map of the connections between the states and what I am measuring. Therefore, C is present at the beginning without multiplying A, and then multiply A up to A, A up to n minus 1. This is a little bit a roughly explanation of the structure. Of course, to be more precise, I have to consider really the mathematical expression. Sarah, I don't know if this possible explanation or description, Mera's explanation, can a little bit help you, at least formally, to understand really in depth. We should to demonstrate the theorem. But of course, if your question was why two lines, formally I clarify because I stop when A is up to n minus 1. If n equal 2, I stop when C multiply A. When I find, C multiply A. Or better to say, when C multiply A, better to say C multiply A is the last line. This is better too. Sarah, I don't know if I try to at least to explain how I can build this. Why I don't go.
Yes. Thank you.
A little bit difficult, I know, because you are not engineer.
No, but I just wondered about the code, and I think now I know the background and I understand it more. Thanks.
Yeah, thanks for your question. Let me go ahead to conclude this now. The function plays solve. My idea was to clarify the function plays, because for the project we don't need to do by hand this calculation. Do you remember last time we concluded almost on this point here, in which I try to explain some sentence related to the eigenvalue, of the matrix A minus LC. And I tried to introduce these calculations. You don't need to learn this, but the idea is to show you how we can also proceed by hand, or better to say what the function place does for us. If I can use the matrix L to place the eigenvalues arbitrarily, of course, if the system is fully observable, the calculation which I have to do are described here. I don't want to repeat everything because we don't need in this for our course or for the goal of this course. But of course, the calculation is not difficult if you remember the determinant, if you remember how we can proceed with the algebra of matrix and vector. At the end, we have a system which consists of two equations and two unknown, because lambda 1 and lambda 2 are the eigenvalues which I can fix as I want, And the goal is to calculate L11, L21, which represent these two elements, the parameterization of the vector could be also in a matrix. This depends on what I am measuring, how many measurements I have. At this moment, I have just one measure, in this case, x1. This means it's just L consisting of one column. But of course, it could be extremely boring to solve this problem here. The problem is to calculate L11, L21, which guarantees eigenvalues lambda 1 and lambda 2. Place realize exactly this. We have in this slide what Place does. Place solves directly this problem here. Of course, here is a little bit strange because the argument of the function Place, which is a MATLAB function, are characterized not by, we can see here, A and C, but A transposed and C transposed. The reason of this is a little bit difficult to explain to everybody because the transposition of the matrix in this case is related to a difficult concept, which is the duality between observability and controllability. But I would like to explain in an easy way to everybody without introducing the controllability and then have to introduce the duality in between. The reason is that Place is built in MATLAB for the controllability. But the concept of controllability, believe me, is a dual concept with respect to the observability. This means I can use this Place also for the observability to build the matrix L or the LC, as I put here. LC because L very often is inductance. Using A transpose instead of A and using C transpose instead of B. P transpose is a formal vector because depends should be in a column. P should be in a column, and then using this again this structure here, I can place, if the system is observable, the eigenvalue, and I can place calculating the matrix L, which basically is the solution of a linear system, algebraic linear system. The demonstration is here, but I would like to skip. There is a formal demonstration, which is also connected with this duality concept. For the engineer, we can speak about that probably in the project, but it's not the goal of the course is more practical. Let me come back, because of more practical, to MATLAB. Now, look, I fixed here a column of the eigenvalues of the observer. Please pay attention. The eigenvalue of the observer is minus 200, minus 500. For the engineer, it's clear that the eigenvalues must be negative. For the not engineer, I would like just to say that we need eigenvalue negative because otherwise the system is unstable. Which system? Observable. The observer. The observer is the system. Please pay attention with its dynamics. And the dynamics of the observer, which is characterized by these two parameters, so two values, minus 200, minus 500, must be, I would like to say, much faster than the system. The reason is easy to understand because I have to observe a phenomenon. I have to estimate, we will see later, estimate the dynamics of a phenomenon. And this means the observer must be much faster than the phenomenon itself. Otherwise, I cannot observe, let me say, in real time because the phenomenon is already past. That's relative expressed in very easy form. But in general, we will see now in the Simulink. Of course, if the observer is fast enough, I can reduce the error of the observation. Do you remember I told you about the error of the observation? Let me calculate, if you want, the eigenvalue of the system. the eigenvalue of the system in MATLAB can be calculated in this form. EIG, eigenvalue of the matrix A. The matrix A characterizes the system. -1, -1. Two eigenvalues, but we have the same values. If you consider -200 is -500, we can see that the eigenvalue of the observer is at least 200 more faster. Engineering understands probably better because larger value of eigenvalue in negative form means faster dynamics. At this moment, I don't want to tell you about this because this is for advances courses. Let me show.
Just one question, just out of interest. So if the observer wasn't faster, or if it wasn't faster, then even if we had one who is there and functioning, it would still not catch the actual
very important
activity.
question. It's 200 times faster than the system. But you remember I told you last time that we are speaking about asymptotical observer. The observer will, in this structure here, will never catch the value. But now we show you with Simulink that nevertheless can be used because practically the difference between the dynamic of the system, the dynamic of the observer, is very small, but not only therefore, I can reduce arbitrarily this difference. Very often we use also asymptotical observer because this is a little bit difficult to explain because in the concept of the system theory. Because the real system is never asymptotical. I mean, if you look at a car that is going free without accelerate on the street, somewhere will stop. If I describe mathematically the system, it could be, if I'm not clever in the description, that the car, the description, the model of the car will never stop. This is the problem of the modeling. Very often, if you don't include nonlinear losses, the car in the description, in the software description, in the mathematical expression, do you remember, now I switch on the lateral camera, the car will never stop. Let me show. But this is the problem of the model. This means if you are aware about that, you can use an asymptotical observer because the system is not exactly well described. This means the observer will reach the value. But of course, very often we used finite time observer, or we use the Kalman filter, which is in its basic structure asymptotically too. But will, how possible to say, will, how possible to say, will oscillate around the value which we have to catch. Of course, we can realize an oscillation also here. And this means also, in this sense, I show you how. In this sense, it could be housed in a Kalman filter. A Kalman filter has many other advantages, but you're right. Let me show you again the concept of last time. For the engineering, I'm going too slow, but it's important. The goal of this course is that everybody can understand. Believe me, it's difficult for me to explain because a bachelor basically, not in all university, just in technical university, we present the Kalman filter or observer or observability and so on. Let me switch on the lateral camera to clarify again. This is extremely important because in the real system, we don't have the exponential behavior. Or seldom we have exponential. Basically, no. We see that the car, if I don't accelerate with my pedal, the car will stop. This means we have very often a problem of the model. Let me go a little bit ahead with this. Let me try to switch on the lateral camera now. How I can do? Here. Last time I was able to do. Let me see. I have to connect something. I forgot to connect the camera. Now we will go in depth on this. It's extremely important in building the model, because Kalman filter can work also with a rough model. In some variables, I can just use some stochastic model. I will introduce also some basic and statistic, as I told you in the first lecture. But of course, we cannot use all statistic model in the variable. I will. You during the semester we will understand better also this concept here. Look at this. You remember this last time? One second. I told you, assuming that is the real system, but of course, in a real system will never stop. If you think about your experience, does not exist. In the life, everything has an end, no? Stop. This means if I say this is the real system, you can say to me, Paolo, but I've never seen a process which never stop. I mean, of course, if you feed the system, of course, in this case, I can understand. If you have a fuel to feed in the car, okay, the car never stop. But of course, also this philosophically, at the end of the universes, we will not have energy. I mean, I don't want to speak about this philosophical aspect, but in the life, everything will stop. Let me say in this form here, but makes sense what we will come back on this modeling build of the model, because it's the kernel very often of everything. If this is the system, of course, again, it's in the system, but in an ideal system, because in life, everything will stop. This is the observer. We can see that we have a mismatch. Now the idea is, may I reduce arbitrarily this mismatch? I will answer this using the simulation, but it's connected with the matrix L. Is connected with the concept of placing to place the eigenvalues. Of course, also here we can get the value if I introduce oscillations. Let me go ahead with the simulation, and then I try to explain this. It's extremely difficult for me because I try to avoid the demonstration of theorem. Of course, also typically this is a course which I hold, not only I, in each university are master for engineering, for technical, also not only for technical, in which we have in a course before this in a course of modeling. But anyway, don't care about that, because I hope that everybody can profit about my courses. Okay, let me look now at the Simulink. Let me explain what Simulink is, and then I will upload in my study the corresponding. This should be this one. Now you should see MATLAB. Did you see exercise 01 sim? What is this dot SLX? The dot SLX is a graphical application of MATLAB, extremely important. In order, what would I like to say, was built to simplify the life to the engineers, and in particular for not engineers, because we will see it is extremely intuitive to use this toolbox here. What is this toolbox? It's not new for us. You remember in my lecture here. If you look here, exactly this scheme here. This scheme is copied. It's not very well copied, because I forgot UIMP is in a photograph. Is not directly editable. Therefore, I did incorrect. But this is U input. This now we will see. These blocks, or these schemes, or in our case, is the scheme is this one. Huh? Better to say, without the connection between x1 and x2. This scheme here, in the scheme copied from Simulink. You remember I told you a lot about that. Block diagrams. Many software, not only Simulink. No? Also in industry, I come from industry, we have also different tools, but MATLAB is a tool very often used. In order to simplify the representation of a system, of the dynamical system. You remember this? Let me show you MATLAB, because if you remember what I told you last time, and now I will reconsider a little bit this language here, which is extremely effective to simulate, to build dynamical system. Now we will see again this block here, or this scheme here, and I will clarify. We will go a little bit more ahead with the concept of the observer. Let me go ahead. Let me go here. Should be this one. I upload for you this simulating file. Let me look if this is really the system corresponding to this M file. M file in our case is not really in the program, but is in the program used as data to generate the matrix particular L. We can see L. Yeah. In some of my lectures LC, because very often I used L as an inductance value when I am considering the motor. Please pay attention, this apostrophe here means transposed. I need to transpose also the function place, because the function place generate a row, but L we have seen must be a column. About that we can discuss during the project. Look at this. Let me share now. Yeah, before speaking, I upload also this in my study. Let me see. Now you can see the nice structure of MATLAB. Excuse me, I put in a different structure, but the equivalent, what I told you last time, the equivalent I will try to clarify now. Let me upload in my study, the software in my study, otherwise I forget. So you can find the material of today in terms of simulation directly today in the evening. Let me see. Is this one? Right. Okay, now you have also the simulating file in my study. Okay. You can see that's a little bit different, this block here, with respect to what? I forgot that probably somewhere I have also exactly this structure here, which I already clarified, but it's a little bit, we can see here, is a little bit, I don't want to say more complex, but we have to work a little bit more. Nevertheless, this kind of representation is almost necessary if the system is nonlinear. About the nonlinearity, I will tell you in the next weeks. At this moment, we are in the cases of linear systems. Therefore, the structure of the matrix A, B, C, D is more suitable because it's more compact. But this form here, we have already seen. Where? Of course, first time is difficult to have in mind. Where is? Let me see. Here. You remember, in linear case, we have this expression here, or these expressions. You remember the concept of the separability between contribution of the state, the contribution of the input, and so on. This allows how to use blocks, or a block in Simulink, which simplify the representation. But of course, if the system is more complex, sometimes it's more difficult to use the matrix A, B, C, and D. Very often we prefer to use this language here in which we separate, we can see contribution x1 and x2 in terms of blocks. Let me express or clarify the structure A, B, C, D, and so on. This block here can be found in the, here, if you look in library browser. Let me share, because also MATLAB is important. Also, just for MATLAB, it's worthwhile to be here, because the course of MATLAB, 2-day course of MATLAB, costs 2,000 euros. here is, let me say, gratis, no? Must be so, because you are enrolled at the university. But sometimes I have to tell you the truth. Sometimes I have here also person from industry is allowed to come here. They told me the chef of the industry, the department, we want to save this money if it is possible to attend your classes. I clarify that my classes is not directly oriented in MATLAB. It's not specific on MATLAB. We use your MATLAB. I try to explain some part of MATLAB dedicated to the project, and then the student learn simulate MATLAB based on my lecture, but of course oriented to the project and so on. But they say to me that it doesn't matter. Nevertheless, could be an introduction also connected with different courses, not only Kalman filter. And then to justify this, we did a project together with this industry. But they save money. Look here, under continuous, look, the block is this. I don't know if you see it. Now I will come back in the Simulink, but here you can find a little bit the explanation. The explanation is exactly what I told you last time. Why the structure, meaning of the structure, and so on. To repeat this, let me come back here. Does reflect exactly what we have in the lecture. If you click twice here, now I share, we can understand what we can use. All connections which we can build manually between the blocks, integral, sum, plus, minus, and so on, which I clarified last time, can be compressed. Very important word. Compressed in the matrix A, B, C, D, and the initial conditions. You remember I told you last time we have initial condition for the system which I don't know. We have an initial condition of the system which I don't know. Basically, you can copy the matrix A, B. Now we need B for the observability, no. But of course, if I have an input here, to test, we have to have information about the input because it's something which moves the system. The observability is independent of B, excuse me. But of course, if I have a B, this means if I have a U, excuse me, U go through the system thanks the matrix B. I don't know if let me share again. Now it's blocked. It's blocked. Excuse me. Let me come back. Let me share my. Oh, it's not better the calculation, but it's a little bit more polite. You can see here. If you remember in the equation, it is repeated here. If I have an input, the input moves the state. I have to estimate the state. This means I have to follow the state. For the observability, it's not inclusive. I clarify many times. Now, the observer, do you remember, is characterized by two inputs. U, if I have U, and the error between what I am measuring, which is characterized by the matrix C. I select X1. And look here, the error between what I am measuring and what I am observing, which is the first X1, if C is 1, 0. Here inside is interesting now, the observer. Why that? Let me share. The observer is characterized again of the matrix A. Of course, assuming that I know perfectly the matrix A, we will see next week in Corazzuse or a hybrid if you remain at home, the limit of the Lundberg observer. I will introduce a little bit after some words about the discrete system. We will come back on the Lundberg in discrete form. That if A is not the same, if I don't know exactly the system, Lundberg, at least in this form, is not so very suitable to estimate. Because you remember the calculation of the dynamics of E, the error, consider that I know perfectly the matrix A, I know perfectly the matrix B. In fact, I put here A, which is the same as in the system, B, which is the same in the system. But the input is characterized. We have two inputs, excuse me. One channel, let me say, of the input is characterized by the matrix L. I will invest today in these 10 minutes, 15 minutes, the matrix L a little bit more. C is an identity matrix because I would like to have the possibility to see not only x1, but also x2. x1, I need to build the observer. x2 in order to verify, to validate the observer. Please pay attention here. The matrix D is a little bit difficult. Do you remember I told you at the beginning that in our course, the matrix D is always 0? Of course, in the practice, it's not always 0. I don't have time really to go in depth on this, but with project, we can do that. It could be that system, often I don't want to say, but it happens. I will show you some example without doing the example, because we can do that in the project. In order to simplify it a little bit, it's not difficult. It's just to identify the matrix D, to clarify what the matrix D is. At this moment, remain with D equals 0. The problem is why D consists of 2 columns and 2 rows. This I didn't tell you when I introduced the matrix A, B, C, D, a little bit, but not so much. Now it is necessary to tell you that the matrix D is characterized by a number of rows equals the number of rows of matrix C. And the matrix D is characterized by the number of columns equals the number of columns of the matrix B. If you look at this definition here, it's easy to understand. Because the output Y at the number of row equals to the matrix, the number of row of C. This means should be the same row also in D. But D is multiplied, let me say, by U on the right. And this means the column of D, in order to do the multiplication, the number of column of D must be equals the number of row of U. The number of column of D, I told you correctly. The number of row of D must be equals the number of, and again, the number of column of D must be equal the number of row of U. And the number of row of U equals the number of B. Now column of B, excuse me, a little bit of column because of this. Basically, the number of column of B equals the number of column of D, because multiply on U, let me say U multiply on the right, B and D. It's more difficult to explain with words than to look at the MATLAB itself. We have two initial conditions. Why that? Because we have x1 and x2. Why 0, 0? Because I assume that I don't know the initial condition of the system. Look now the simulation. Probably it's better to discuss everything again, use the simulations. Do you remember L is calculated such that, let me eliminate this problem here. This is the noise, which we will see next week. Consider the problems which I have with the Lundberger observer. L is such that the eigenvalues of the observer are -200, -500. Let me run. Simulink, again, is a graphical interface of MATLAB. If I run is basically just click on this row, and run means I will find the solution. Please pay attention. Run means find the solution of this relatively complex system, which consists of a real system, which is this one, simulated this one, and an observer, which is designed here. Please pay attention. What is here is in the microcontroller, in the computer. What is here is the real system. Could be a motor, real motor. Or could be also in software form and a description of the bank system. Could be a description of the COVID system. Look here. I will compare here we can see here, no? The real x2 with the observer is 2. Let me show you. Result. We can see that at the beginning we have the differences because we have a difference in the initial conditions. Of course, if the initial conditions is the same, I assume that I know perfectly the system. I don't see differences between the real system, let me say x1, x2 in the real system, and x2 observed. But this never happens, that the initial condition is the same. But never happens also that I know everything of the system. We'll discuss next week about that, because this is important to introduce the Kalman filter. It seems that I will reach the system, but of course, excuse me, the variable x2, but it's not valid with my sentence, because of course we have the resolution of the computer, but we can see that practically, yeah, of course, here also some calculation error occurs in the machines. But a little bit, if you look from this point of view, we can see this asymptotical behavior. Now, as I told you, what happens if I generate oscillation? How I can generate oscillation? If I can generate oscillation, let me say, the estimation nevertheless remains asymptotical. But of course, I will move, let me say, roughly speaking, up and down on the real system of the real variable. Let me show you what I intend practically with MATLAB. It means how I can generate, where is now? Where is, yeah, oscillation. For the engineer, it's easy to remember that if I put here complex eigenvalues, if you remember in math, it is possible here to put, yeah, because we have 2 eigenvalues. Of course, if I have just 1 eigenvalue, it's not possible. It remains nevertheless asymptotical, the observation. But if I have at least, let me say, more than 1, it's always possible to put Mutawan said, it's possible to put complex eigenvalue. Must be conjugated. I don't know if you remember this concept here, the engineer. For not engineer, it's a little bit too difficult to express this, but should be conjugated. This means the real part must be this, must be the same, must be conjugated. Gauss theorem. Look at this. What happens now? I don't know if it's able to recognize J. Otherwise, I don't remember. Let me see here. I think I is the complex variable. I don't know if you remember in gymnasium. It's not necessary to learn this now, but just to show you that if I put some coupled, let me see, excuse me, I have to run. I click wrong. I don't know what you see now. Okay, now MATLAB. If I run now MATLAB here, we have 2 complex eigenvalues. Conjugated means plus J minus J. Look now what happens in the simulation. If you remember, with complex eigenvalue, we have oscillations, the solution of a differential equation. Let me see if this oscillation is enough to show you this effect. It seems to be a little bit much better. Because remains asymptotically. In fact, we can see that we will never achieve. But theoretically, at least here we have an error in of course, in the competition. But earlier, we can see that we go up and down. Let me see, down and up. Now we can see here oscillate around the solution. This means, of course, I will reduce asymptotically, but somehow I have the feeling that I will reach the solution. Excuse me, I reach the value which I want. We will see in Kalman filter this structure a little bit better. The last sentence now, the speed of convergence. I told you I can speed up as I want. Look at this. Here, let me say, it seems to be relatively fast, but I don't want to go really in depth here. With a picking problem, with at the beginning, we have an error. This is due to the fact that I accelerate too much. I accelerate too much. The system, the observation, the observer is not optimal. We will see Kalman is optimal. This effect is a little bit not so extreme. But in order to show you the effect of L, let me place the eigenvalues, smaller eigenvalues, even though negative. Let me show you. In order to slow down the estimation. Why I need to slow down? It could be that this error at the beginning, disturb me for different reasons, because at the beginning I have a really uh, uh, wrong estimation. Now we will see that the estimation at the beginning will be a little bit better, but I need more time because I reduce in absolute value the eigenvalues of the observer. This means the observer will be slower, but at the beginning more precise. Look, here is what we have. 700 I'll speak, and we will achieve the results, at least acceptable results, at what time? 0,05, let me say, no? Now, what happens with the new values? Let me run. You can run here. I don't know if you see the picture. Run. You see run, of course, no? I don't remember if I share. I hope yes. Look. You can see that is not 700, but something more than 60. And here, a little bit slower, no? I don't remember what 0, comma, I forgot. Not so slower. What 0,5, similar, or the 0,05. I don't remember. But in any case, let me redo because I forgot the values. Let me redo as before. Now is 0,5. Let me say. If I put 200, let me run. Let me come back now on MATLAB. Now try to memorize 0,5. In any case, the amplitude is reduced as before. Let me look now what happens. Yeah, 0,05. This means, of course, we pay the price, no? Because in order to reduce the initial error, because it could be that disturb me, it could be in control, or that to be precise in the monitoring. But of course, I have to slow down also the estimation. This is a little bit to play with this value here. Of course, we will see that the Kalman filter is a little bit easier, I would like to say, to manage this kind of problems. Because the observer is an optimal observer. This means try structurally to optimize this aspect here. But of course, also there we have to tune. Anyway, we have some problems. But in any case, is stronger the Kalman filter. The last sentence, which is in the introduction of the lecture of next time. Of course, I will show you also the discrete form very shortly, introducing the discrete system. If I have a disturbance here, I don't know how strong it is disturbance, but in general, we have some problems because until now, I didn't consider any disturbance in my mathematical, let me say, analysis. Look, of course, sometimes it's not acceptable to have some kind of spikes. Kalman filter can help also in this case. Kalman filter can help also when I don't know exactly the parameter of the system. Here, I assume that the parameter of the systems are perfectly known. If I put the same initial condition, I don't see any difference between the x2 and its observed variable. Okay, I think for today I will conclude. I will stop now to record, and then we can open the discussion. But if you want, I can continue to record also your question. It depends on you. It's not so. I don't have any problems. It could be useful also to record also the question if you agree, and it's not so, can help also the students as you want. Okay, probably we can record it because the idea to do this YouTube channel is not for me. For me, it's more work. But I think which is the people is not present. If you don't have problem to pose questions, I can record also questions. Okay, question
So
me.
so just regarding the YouTube channel, will you send us a link or a message
Yeah,
when
yeah.
you okay, thank you.
As soon as I read a little bit, it could be that I need the help from some of you. I will ask, and then I will send you the link. It's free.
Yeah.
Don't say that you have to pay. You will not, never, nobody should pay. Absolutely, because I will lose the job. It's clear, it's clear. But you can see that everybody can download or to see again directly in YouTube. No, nobody should pay
Okay,
me there. In any case,
thanks.
I can defend me because it's free, totally free. It's allowed to do.
Okay,
Sometimes it's really suggested by university. I received many requests,
yeah.
but must be free. I will be free.
Okay. I just want to say I'm a digital media student, so if you need help regarding YouTube,
Ah,
I can help you.
yeah,
Yeah.
thank you, Sarah. No, you, Sarah. Thank you.
Mm,
It could
of
be
course.
that I need you. You know that when I read again when I look my video, when I hear again my video, I have a strange voice. Really, I don't know how I can manipulate a little bit in order to have a. It's a very metallic. I don't
Mm,
know how you hear my voice, but if you hear my
mhm.
recording video, it's very metallic. It is not so
Okay.
nice to hear.
I
But
think it's fine, but I mean, it's always on Zoom like that.
do you remember last time I tried also with this, but no changes.
Yeah.
Sometimes I use, sometimes no, because it sometimes disturb me a little bit.
Mm,
But anyway, we can. And next week I will be in Lüneburg in Koratsu's room. The lecture remains nevertheless also hybrid. It's hybrid. This means you can stay at home if you cannot come. But I would like to invite everybody if it is possible to come, even though from home is the same as today. Then we can discuss how we can organize also the material better, slide, and also YouTube channel. Thank you, Sarah. Very nice from your side.
I mean, thank you for doing the video. So,
I think can help, even though
yes.
sometimes I say the students don't come absolutely, or they don't pay attention. That say I can look at the video, but I think the advantages are more than the disadvantages, or that the drawbacks. This means I will do that. In particular, if you help me or somebody can help without together with you, we can do it probably in the best way because I'm not so expert in such kind of tools, I would like to say. Technical question. Thank you, Sarah. Yeah, technical questions or any kind of questions. But next week we can do probably if you come, no? But also now. It's not okay. If no question, we will see next week in Corazzuse, or if you remain at home, the same address, because it's possible to hold the lecture hybrid. It's also possible online, but anyway, I like to be present. I will be in Lüneburg because my permission to be out is almost finished. But nevertheless, I have also the permission, but I will be in Lüneburg. This means I will be there. If we can meet in Corazzus, okay. Otherwise, as today. parallel hybrid. Thank you. I hope I was not boring. Thank you.
Thank you. See you next week.
See you
Bye.
Ciao.
Bye-bye.